So for more complicated things that deal with exponential equations, we essentially do the same idea, but in order to get things in terms of the exponents, we need to use some logarithms. So we have some steps that we can follow here to get there. That we start by isolating the exponential expression on one side as best we can, then take the common logarithm of both sides if we have base 10. If we have anything else, we use the natural logarithm. Then simplify using exponential properties, maybe the product and quotient rules as well in some cases, and then solve whatever is left over, where what we get left with after those processes is stuff in terms of, well, chapters 2 and 3, or a little bit of 1 as well. That is, we're going to be dealing with things in terms of rational equations, or maybe some square root equations, but usually linear and polynomial things. Where actually, in that last example we did there, we technically could have written in that extra step of dealing with logarithms. Technically speaking, we could deal with, like, say, log base 4 for the first one and log base 3 for the second one to isolate our values there and turn things into log base 3 of 3, log base 4 of 4. Those are both 1. That's really what happened there, which is why I said we're abusing the one-to-one property and the logarithmic inverse property there. But it's a lot of extra work to write that out for every general case to make it look more complicated than it really needs to be, where all you have to do in those is just identify the exponents. For stuff like this there, we have to be a little bit more clever, but really the process is much the same, except we're going to write out that hidden step in the middle, and our answers are going to look a little bit less pretty most of the time. But anyway, let's take a couple examples to see how this actually works out. For this, we want to solve the exponential equations 3 raised to the power x equals 151, 10 raised to the power x equals 9001, and 7 to the 2x minus 1 equals 3 to the x plus 1. So if we want to deal with that first case, we have the 3 raised to the power x is equal to 151. Since we don't have this in base 10, we'll just use the natural logarithm. The natural logarithm is what you can use for anything. It's just that if you have 10s anyway, you might as well use the common logarithm. So here, we'll take the natural logarithm of both sides. Oh, not 3x. We could use 3 raised to the power x is equal to the natural logarithm of 151. And also, we could use log base 3 there. It's just that we like the natural logarithm more for reasons. And again, it would be a little bit subtle. It would make the thing more difficult than it needs to be if we said, hey, pick the logarithm that best fits, especially for something like that third example, where you could either do log base 7 or log base 3. We don't like to be as ambiguous as all that. But hey, if you like a different method, why not? Anyway, for this, we're then going to make the best of our situation here, pull out the x. We get x natural log 3 is equal to natural log of 151. So x is equal to natural log of 151 over natural log 3, which is the exact answer I'd normally be looking for, but just to be sure, so you have a better sense of what that is, it's going to end up being about 5.512. Then for our second example, we play a similar sort of game, except there, because we have 10 raised to the power x is equal to 9001, it is over 9000, I suppose, we would identify that the common logarithm fits better for this case. We could still use the natural logarithm if we prefer. We don't need to use the common logarithm. We could use the logarithm base 8 if we really wanted to, but why not be consistent? Anyway, we'll take the common logarithm here just because it makes things a little bit prettier. So we get log base 10 of 10 raised to the power x is equal to log base 10 of 9001. Log base 10 of 10 raised to the power x is just x. So we get x is equal to the common logarithm of 9001, which again is fine for me. I like the exact answer, but usually people like to know what that sort of thing actually looks like, where this would be about 3.954. And hey, just for review, that should make sense, right? Because we're talking about the common logarithm of a thing. We're identifying a number of powers of 10. 10 to the fourth is 10,000, so 9,000 should be a little bit less than 4 in terms of the common logarithm. Yeah. Maybe that makes sense, maybe it doesn't. takes a little bit of thought. Anyway, for our last example, for our third one, we're dealing with a case where we have exponents on both sides. And because we have exponents on both sides, we don't have the sort of leeway there to say, oh, maybe log base 3 makes sense, maybe log base 7 makes sense, either makes sense for one but not for both. And that's why we just default to the natural logarithm, at least part of why. So we're going to take natural log of both sides, and I'm going to save a little bit of space here because you're going to see the same sort of thing happens, that if we take the natural log of both sides, we'll get 2x minus 1 times the natural log of 7 equals x plus 1 times the natural log of 3, where again, if we take log base 7, that guy's a 1, log base 3, that guy's a 1, and then we'd basically be having the change of base property thrown at us implicitly, but we just use natural logarithms because it's nice to have a consistent process. Anyway, from there, it's a lot of reorganizing, some rejiggering is going to go on here, and unfortunately I'm very low on space, so I'm going to skip a couple of steps in here in terms of multiplying out that 2x minus 1 and the x plus 3, and what I'm going to end up getting here if I pull over a log 7 and pull over an x log 3 will be x, and you can check this for yourself just to be sure. Like I said, I'm short on space, times 2 natural log of 7 minus natural log of 3 is equal to, the natural log over here is going to end up being log 3 plus log 7, which you use the product property there, and that'll turn into the natural log of 21. So if you want to take this even a half step further, which I would, you can pull that 2 into there, make it a 49, minus 3, it gets 49 over 3, and you would have x is equal to the natural logarithm of 21 over the natural logarithm of 49 over 3. Where if you want to write it otherwise, you could say that this is, for the same reason, the natural log of 7 plus the natural log of 3 over 2 times the natural log of 7 minus the natural log of 3. If that's more logical to you, by all means, I'm not picky about it. Either way, you should end up with a final answer that is about equal to 1.090. That's about 1. And this is essentially how we handle exponentials. We deal with things, we throw in some logarithms, get rid of our exponents, and we end up where we're supposed to be. So, if we want to deal with logarithmic things, we take our logarithms and throw in exponents and end up where we want to be. It's the reverse. Do the same thing in the other direction. We'll see that next.